So we've been talking about the leverage points of climate change, and our conclusion was that they're really easy to identify, but very hard to change. So that's exactly where a systems model, like this one, can come into play. Let's look back at our model. The real dynamic that we're talking about is too much energy leading to too much temperature. And the reason that we have too much energy is too much greenhouse gas accumulation. But let's get creative. Let's broaden our perspective a little bit. The energy leaving the system here is only 1/2 of our stock and flow. What if we could intervene some way in the solar radiation striking us? What if we could come up with some variable, something we could do that could actually block incoming solar radiation? And the thing that's driving, this is the thing that's driving the energy accumulation. If we could block enough of it, we could offset the increased energy being trapped by the greenhouse gases. And what if we took the same approach, but to the carbon being trapped in the atmosphere? We could produce less of it, but what if that's too hard? What if we absolutely have to drive everywhere and have to charge our iPad every single day? Well, we could look for ways to increase the uptake of carbon dioxide. We could find a way to make that uptake happen faster and take the greenhouse gas, the extra that we were producing, out of the system. This is exactly what proponents of this thing called geoengineering are suggesting we do. And the approach has been referred to as hacking the planet. And it consists of two main sets of strategies. And the first one is called solar radiation management. And in solar radiation management, the idea is that we use technology to somehow take the amount of energy that hits the Earth in the first place and reflect it back out into space so that it never gets accumulating at the Earth's surface. And this is where we find some of the goofier ideas that are out there. Giant sunshades that are assembled in space, clouds of mirrors floating around the Earth in orbit. More realistic proposals have to do with changing the characteristics of the atmosphere itself. That is, manipulation of the content of the atmosphere so that it reflects more solar radiation back out into space. Could that work? Let's look at a historical example. In August of 1883, there was a volcano in Indonesia, and it was called Krakatoa. And that volcano erupted, it exploded. But it wasn't just your run-of-the-mill volcanic eruption, if there's such a thing as a run-of-the-mill volcanic eruption. It was a massive volcanic event. We know that the explosion was heard thousands of miles away. Cubic miles of rock were thrown up into the atmosphere, and the waves caused by the event went around the world and were detected off the coasts of England and France, according to a Royal Society study that was published a few years after the event. But the effect that we care about is the effect that happened on the atmosphere. The same Royal Society observers, looking at a compilation of reports from around the globe, described the appearance of a sky haze that spread throughout the tropics and that by November of 1883 had reached the United States and Northern Europe. And this haze, which we now know was fine particulate matter ejected from the volcano and suspended up in the air, caused phenomena such as coronas around the sun, intense sunsets, a perceived dimming of the moon, and the disappearance of dimmer stars from astronomical observations. This happened worldwide for at least the next 2 to 3 years as the material slowly settled out and sank down to the Earth. So that's pretty spectacular stuff, right? But what else happened? The really important thing here is all of that material suspended in the air actually caused solar radiation to be reflected back into space. And the next year, after the eruption, the temperature of the Earth was 1 degree Celsius lower because of the radiation that had been blocked from coming in because of this volcanic haze. And it turns out that when we go back and look, we can see that this pattern of cooling of the Earth's temperature following a volcanic eruption is one that recurs repeatedly throughout history. This is the effect that geoengineers think that humans can replicate. To create a haze in the atmosphere, create an artificial volcanic eruption. And of course, we don't want to create a big explosion, but one technique for doing this is to take an airplane and load them up with a class of sulfur chemicals known as a sulfate aerosol. And we take those sulfate aerosols and we spray them in the stratosphere, high up in the atmosphere. And researchers estimate that this could be carried out for less than $1 billion, and we'd repeat it once every 4 years. And it would have the potential to reduce incoming solar radiation by around 1%, which would be enough, we think, to set off at least the current amounts of anthropogenic emissions. Other researchers have proposed that we can do a thing called cloud whitening. And cloud whitening involves using a fleet of unmanned, self-propelled ships, solar-powered, that would sail around the Earth's oceans and pump water into the cumulus clouds above the ocean. Simply by making these clouds denser and therefore whiter, think big white fluffy clouds, it would increase the amount of solar radiation that was bounced off of the upper atmosphere. The second technique, which is called carbon dioxide removal, similarly has some more and less realistic versions. Ideally, we just sweep carbon out of the atmosphere, right? We would just have a big machine, a vacuum that just sucked specifically the carbon dioxide molecules and stuck them deep underground or something like that. But we don't currently have any technology that can do that. We can imagine some representations of it, an artificial tree out there sucking carbon dioxide, but we have nothing that's actually currently more effective than a real tree in doing that. And so that brings up the question, why build fake trees when we have real trees? So one way of combating climate change, it's long been recognized, is simply going out and planting vegetation where vegetation has been cleared. We go out and we plant more trees, it takes carbon dioxide out of the atmosphere, turns it into wood. If we manage that wood well, turn it into furniture, right? Think of some antique piece of fine wood furniture. That's carbon dioxide that's been taken out of the atmosphere and will last hundreds and hundreds of years in a human usable form. So that's one technique. So reforestation contributes to greenhouse gas reduction, but another thing that geoengineers have talked about is the increasing uptake from the oceans. So in ocean food systems, carbon is taken up by algae, and algae have very, very short lifespans. You might remember this from the eutrophication videos earlier. As algae grow and die, they sink to the bottom of the ocean, and once they're down at the bottom of the ocean in that very cold water, the carbon dioxide can become locked up in the ocean sediments where it's taken out of the atmosphere, those for a long time. So some of the carbon bubbles back out as carbon dioxide after the algae die, but some of it goes to the ocean floor. And it turns out that algae in the ocean are very nutrient limited. And in particular, algal growth is known to be limited by the availability of iron. So one suggestion has been that if we could fertilize the ocean with iron, that we could create a big boom in algal growth. So we add iron to the oceans, it increases carbon dioxide removal by increasing algal growth, we get more greenhouse gas uptake.